All right, hello and welcome to this piece on solving for first price sealed bid auctions using revenue equivalence. Let's jump straight into it. We load some things here, and here's just a general reminder about how to use linear interpolation, which you can use look at your own leisure if you get confused later about the use of the interpolate.interp1d function. All right. Let's start by looking at the revenue equivalence and see if we can illustrate it. So we're going to draw a whole bunch of different samples. Each time we're going to have 5 bidders in our sample. They're going to have uniformly randomly distributed valuations. And as we saw in the lectures, the solution to the Bayes-Nash equilibrium in a first price sealed bid auction is to bid n-1 over n times your valuation. So lambda star here is going to tell us what if I am a bidder, my valuation is 0.8 and we are 4 bidders. What should I bid? I should bid 0.6. What if we're 10 bidders? I should get much closer to my valuation. All right. So let's continue here. First off, we have this neat little function here, which gives us the argument of sorting V. So actually, if we go np.sort of v, then we get the same as writing, taking the argsort that gives us idx, and then take along axis of v evaluated at idx. So basically, this is just evaluating v at the index given by idx along axis 0. So in other words, let's just review. idx.shape is 5 by 100,000. It looks like this, and this is giving us, it's telling us that here for the first set of valuations, for example, let's just redraw the valuations. V, let's look at the first sample that we have. What it's telling us is we have to take the 0th is actually the smallest one, and then 1 and 2, and then it says 4 and 3. Oh, that makes sense because the last element is actually smaller than the second to last. So this is telling us how to sort that array. And what we're doing is then we're taking these B, which is now we've evaluated B star at V. So these are the bids, the optimal bids. We're also sorting them in the same way. This actually does the same as sorting B, which you can check on your own. And then we also create this helper variable, II, which tells us what is the bidder identity in each of the positions so that we know who won the auction after having sorted the arrays. Then we can take here, what does the winner pay in a first price sealed bid auction? Well, that's just the bid corresponding to whoever had the largest valuation, and that's what is in the final row of B. And we can ask, what does the winner pay in a second price sealed bid auction? Well, there the winner pays the valuation of the second guy, or rather the bid of the the bids in a second price sealed bid auction are actually the valuations. So the bid of this the second highest valuation type is going to be the value of the second highest type. So this is what the winner pays in a second price sealed bid. All right, so let's just have a look at what the payments look like in those two auctions, because they're probably going to be different. So we loop through first, what does the winner pay in a first price sealed bid? What does the winner pay in a second price sealed bid? And we do a histogram of this X variable. And what we can see is that in the first price sealed bid auction, nobody ever pays more than 0.8. But that makes sense, because if we evaluate B star, the optimal bidding function, at a VI equal to 1.0, the maximum you can possibly have, and given the N that we do have in our auction, that's 0.8. So no one can ever bid above 0.8. But of course, in a second price sealed bid, what you're paying depends on what the second highest type valuation is. So it's possible to draw, we actually did find auctions apparently in our simulation where the highest type was here and the second highest type would have then been very close by So the highest type was someone up here, and then the second highest was here. So of course in a second price seal bid you can end up paying higher. You can also end up paying a lot lower in the second price seal bid auction. So the distributions look different. But what we're also doing here is we're also printing something else. We're printing x.mean. So we're also going winner pays the vector that we created, but just before, what is the mean of that vector? And we say what is the winner pays matrix in the second price seal bid auction. And we can see that those two numbers are incredibly close to each other. Oops. And we should rejoice in our hearts and minds because that's what the revenue equivalence theorem says. So that's good. They're different, but that's due to sampling noise. So if we were to increase R, these two numbers would get closer to each other. It's something that holds in expectation, revenue equivalence. All right, so now let's do a little bit more plotting. So what we're going to do now is what we want to show. Let me show you the graph first, and then we can talk about how we construct it. We're going to have on the x-axis the valuation, and on the y-axis the bid. And we're going to be comparing the second price seal bid to the first price seal bid. And so first off, what we can note is that in the first price seal bid auction, which is the orange line here, if you have a valuation of 0.6, there's no distribution. You always bid the same amount. So, which is given by B star of 0.6 with the number of bidders that we have. So you always bid 0.48. There's no, there can be no, and that's what's out on the y-axis here. There's no variation there. But in the second price seal bid, as we talked about, if this is your valuation, well, then there's a full distribution around that of different valuations of the second highest type, because they're just independently distributed uniforms. We've conditioned on a uniform being smaller than or equal to my valuation, but there's still a full distribution around it. So what that means is that all these green little dots here, those are all of the observed payments. The actual bids, you can't see the green one here because it's too small, but the green ones are the actual payments that ended up getting paid. So you can imagine that there's a whole histogram around the blue line. And what the blue line shows is the average of those data points. So you can imagine the histogram around the blue line, and we can compute the average, and that's what's in here. So what this is showing us, and here's how it's done in the plot. We use stats.bin statistics, and what that does it takes the x variable here, which is the valuation of the highest type, and chops it up into 20 bins, and we can look at actually what the bins look like. The bin edges are given by these numbers, so from 0.1 to 0.146, for instance, that's the first bin, and it computes the average of the y variable, which is the valuation of the second type, for all observations where the x variable fell inside of this bin. Annoyingly, this means that there are 21 bin edges, right? There are 20 bin edges to get 20 bins. So what this little snippet here does is it takes the average value of the bin edges and puts that as the x variable here in xx. So then that means that xx in the first number here is 0.12. So that is the average of the two first bin edges, 0.10 and 0.146. All right, so this is showing us that if we take a bin around up here around 0.08, then on average those payments in the second price seal bid were equal to the payment in the first price seal bid. So that's giving us another show at the fact that this result that the average payment was the same or very close within simulation noise difference between the first price seal bid and the second price seal bid. That result does not just hold when we take the overall average of those two vectors, it also holds if we chop up the data set into bins of the valuation. And to just give you a bit more insight into how we use these sorted arrays, I wanted to just show you how you can put these sorted arrays into pandas data frames, and perhaps that makes it a little bit easier to look at. So what we do here is we take in the outset, V is a matrix that's it's a very wide matrix and not very tall, and that makes it hard to look at in pandas because we have to scroll sideways. So I'm just going to transpose it and transpose the bit matrix as well, and stack them next to each other horizontally, and then I'm going to create labels V0, V1, V2, and so on, and the same for B. And then I'm going to call the index R, lowercase r, and then here's the matrix or the data frame that we've created. So you can see the replications, the draws, the samples are going down here, and here you can see the valuations. And as you can see, each of these rows have been sorted. That's what we did when we used the arc sort and take along axis. So they're increasing. So V5 is always the largest number. And so what we can do is we can say, let's take all of these values. So note that V is a list of variables. So we can take that of V, that's those variables. The entire matrix also has the entire data frame also has the bits, right? Take the maximum along the first axis and just look at the first couple of ones, and what we can see is the first one is 0.9917, and so that's the same number which is here, and 0.58, and that's the number which is here. So that's great. So it's actually giving us the same thing as if we just took that of V5, which is the maximum. So this gives us the average maximum, and this is the average of the second highest valuation. And now let's look at the bids. They're sorted in the same way, and what we can see is that the average of the highest bid, which is computed using the first price sealed bid rule, is the same as the second highest valuation. So so that's how to think about what we've done. We've drawn these samples where there are 5 bidders in each of them, and we've done it a lot of times. What we can do is we can also look at the bottom of the matrix, and you can see the last one here is R equal to 99999. So that's the 100,000th draw we did. So this is how to think about the largest values, right? So that of V4, that's the second highest valuation, and we computed the mean, but we can also plot it if we wanted to, and just look at what the distribution of the second highest bid looks like. Okay, so I hope that helps a little bit. Okay, I'm going to break the video now and have a second one where we do the remainder of this note.